Hi everyone. Today I want to talk a little bit about plate tectonics and page 5 of the ESRT. So, to begin, we're going to have three different kinds of plate boundaries. We are going to have a transform, divergent, and convergent plate boundaries. So, in this video, I'm going to take you through each one as well as where to find them around the world. Before we get to that, I want to look at page 5 of the ESRT where we have this world map and it has our plate tectonics information. In addition to the plate tectonics information, we also have our latitude markers on the left and right hand side. These are going to measure north and south. With highlighted in red here, I have my northern values that are north of the equator, and in blue here, I have my values that are south of the equator. There's my equator line, and then here are lines building up north and south as I work my way to the poles of the Earth. In addition to latitude, I have longitude. Here are my markers at the top of the screen. In addition, I have them at the bottom of the screen. Now, this measures east and west, and it measures east and west of the prime meridian, 0 degrees longitude. So I put another marker at 180 degrees longitude, and that's because when you cross this marker, we switch from east to west or west to east. Now in blue up at the top, I have where our western values are going to be. So what I would like you to notice here is that the entirety of North America and South America are always going to be western values for our longitude. And then here in red, I have where our eastern values of longitude are going to be. So I have a question for you. Where is Hawaii? What could you assign its lat and long values? So if you're watching on YouTube, pause the video and figure out the lat and long based off what I was just telling you. And I'm going to show you the correct answer right now. So here's Hawaii in our beautiful little heart. And if I take two lines, here's going to be my latitude line, here's going to be my longitude line. I'm sitting on 20 degrees north latitude and close to the 160 degrees longitude. So I'm going to call that 155 degrees west. So in general, Hawaii sits at about 20 degrees north, 155 degrees west. If you need a refresher on latitude and longitude, please check out my previous video. Now, when we talk about plate tectonics, we got to understand why the plates move around the world. And what's happening is we have convection currents in the asthenosphere, the partially melted area of the mantle, that as we get the rotation of the convection currents, the lithosphere, aka our crust, is getting pulled along with the movement of the mantle. So again, just like before, if you need a refresher on convection currents, check out my page 10 breakdown video, and I'll link it in the description below. So getting to our plates and our plate boundaries. First one we're going to talk about is our transform plate boundary, where we're going to have two plates that are not moving towards or away from each other, but they are going to be moving side by side. So on the left here, we have plate 1 and plate 2, and our arrows are going opposite directions from each other, but they are parallel. So where can you find this on the map? Before we look at anything on the map, what I want you to check out is down in the key at the bottom. We have our transform plate boundary symbol. So anywhere on the map you see these arrows that are parallel and going side by side, that is going to be a transform plate boundary. So what I have for you here is I circled the San Andreas Fault in California. We have these markers going side by side, showing us that we have a transform plate boundary in this location. Here are a couple other transform plate boundaries, and they are found all along the world. We have one found in New Zealand, as well as down near Antarctica, near the Scotia Plate. So I'm going to pause here And I'm going to allow you to take some time to answer this question from an old Regents exam where it's asking you, most of the tectonic plate boundaries of the Scotia Plate are classified as. So look over A, B, and C and D and decide for yourself. And in a moment, I will explain how I got my answer. So if I zoom in on the Scotia Plate, it's a touch blurry. What I can see is I can see these arrows parallel to each other and moving side by side. So I do know from that and from the key below that this is indeed a transform plate boundary. To decide on my direction of travel here, I want to look at my arrows and their position on this map. They are pointed towards the east and pointed towards the west. So to decide between A and B, I'm going to go with A because these transform plate boundaries are moving to the east and moving to the west, our left and right hand sides of this map. The next plate boundary I want to talk about is a divergent plate boundary. So a divergent plate boundary is when two plates are spreading apart from each other. We have that convection of the mantle coming up to the surface and pulling our plates apart from each other. In most of the examples of this found, if not every single example around the world, both of the plates involved in divergent boundaries are going to be oceanic plates. Now, when we check out our map, we are indeed going to have a divergent plate boundary symbol at the bottom. So divergent plate boundaries, the most noticeable aspect of them are going to be that the arrows are pointed in opposite directions from each other. Now, one of the most prominent divergent plate boundaries in the world is the Mid-Atlantic Ridge, as well as some other ones like the East Pacific Ridge and the Southeast Indian Ridge that I have boxed for you on the map here. Now, that word ridge is incredibly important. A ridge will only ever be used for a divergent plate boundary. That is a term specifically used for when plates are being pulled apart from each other. So again, here's another example of a question from a Regents exam where it's asking you, base your answer to the following question on the map below. Letters A through F are locations on Earth's surface. Which location is closest to a divergent plate boundary at an ocean ridge? So we know it's a divergent plate boundary and we're looking for some sort of ridge. Use page 5 of your ESRT, check out all the different locations, and see what you can come up with. So it is indeed A, and I'll show you why. Now, if I zoom in near the North American plate on our page 5 of the ESRT, what I can show you is down at the Cocos plate near Mexico, we have the symbol for divergent plate boundaries. Now, ridge is not labeled here. It won't always be labeled, but you do have your symbol available to you to use to come to the conclusion on why this is indeed a divergent plate boundary. If we look at the other options, if we look at B, those are going to be convergent plate boundaries, something we'll talk about momentarily. C, no plate boundary exists there. Same with F and E. And then D is interesting, and that is mainly going to be a transform plate boundary over at D. As we continue to talk about divergent plate boundaries, I want to talk about that convection cycle a little more. So here's a snapshot from the gizmo we did in class where we have the convection current coming straight up to the surface of the oceanic plate. Now, as that continues to rise, it hits the crust and it starts to spread out. So the mantle is moving outwards, pulling our lithosphere outwards with it. As we continue to move outwards, this magma gets to the surface and cools. When magma cools, it creates new rocks. Now, we have these bumps on the side. So as the lithosphere moves out from each other, those new rocks that were once created at the center of our divergent boundary move away from the center. So when we talk about the ages of rocks at divergent plate boundaries, we are going to have the youngest rocks at the center. These are just being formed. And then we are going to have older rocks the farther we get away from the divergent plate boundary, because these rocks were created in the center, but then over time spread out to get farther and farther away as the lithosphere moved away from the divergent plate boundary location. Here's another example of a Regents question that is involving divergent plate boundaries. Check it out. We have a cross section, a look inside the crust of the Earth, 4 locations, and we're trying to find where the youngest rock is here. So take a moment, see what you can do. Now, what I want to focus on here is that word ridge. Ridge is always associated with divergent plate boundaries. So I'm going to go with C, because when we look at this term ridge, that is going to be where the center of our divergent plate boundary is. And what's really cool is C is built up a lot. It's up higher than A, B, and D. So we have magma coming up to the surface and stacking new rocks on top of each other. So magma is rising here at mid-ocean ridges. It cools and makes new rocks. And then the farther we get away, the older the rocks are going to be. So we have really young rocks at C, and then B and D, relatively similar ages, and then A are going to be our oldest rocks here, the farthest rocks away from our mid-ocean ridge. The next kind of plate boundary I want to talk about is convergent. And convergent are super cool, and they are going to be making our volcanoes and something known as a ring of fire around the world. So in a convergent plate boundary, we have 2 plates colliding. That's where that word converge comes from. So 2 plates are converging or colliding here, and we get this thing called a subduction zone. So a subduction zone, if it's circled down in this picture, is where our oceanic plate is sliding underneath the continental plate. And that's happening for one very specific reason. The oceanic plate is denser than the continental. It has a density of 3.0, while continental crust has a density of 2.7. And the good news is you do not have to memorize that. It is labeled for you on page 10 of your ESRT. So our oceanic plate is being pulled underneath our continental here, also known as subduction. So jumping back to page 5, we do have our convergence symbol down here at the bottom. In addition to our symbol, we have the subducting plate labeled and our overriding plate labeled. The subducting plate is going to be the oceanic, while the overriding is going to be the continental. On the side of where the rectangles are will always be the continental or the overriding plate. The example I want to use here is the Aleutian Trench. It is a part of the infamous Ring of Fire that is this circle that goes from Eastern Asia and Australia to Western Americas, all the way down into Chile. So where we're going with this is this word trench. Just like ridge and divergent boundaries, trench is going to be our key word for a convergent plate boundary. Trenches are the deepest, or the deepest parts of our oceans. So the farthest we can go in our oceans. That's because our ocean plate is sinking below the continental, making these very deep areas of the ocean. Now, you can have places on this map that are convergent without having this word trench, like here where India meets Asia. So India, a subcontinent, is slamming into the Eurasian plate. And what's happening here is something I'm going to show you in the next couple slides, is we are creating the tallest mountains in the world here, the Himalayas, by colliding 2 land masses together. What's really cool about India and Asia, when they hit together, these are both continental plates. So we're not subducting, but rather just colliding here. They are both the same density, therefore we are not pushing one plate underneath. So here's a quick question for you about convergent plate boundaries. Take a moment, see what you can do. Okay, so right off the bat, how I attack this is when I look at my answers, I see two of them, A and C. They got the words ridge in them. Now, ridge associated with divergent plate boundaries. I'm going to scrap those right away. So I'm down to two answers. I'm down to the Aleutian Trench and the Pacific North American plate boundary. So the first one I'm going to focus on is the Pacific Plate North American plate boundary. So I've circled my Pacific Plate and North American Plate. These are really huge areas. All of the Pacific Ocean, all of the North American continent. So although it seems like a nice answer, because we do indeed have the Aleutian Trench here, we have this convergent boundary right here. What I don't like about it is there are areas where we have a transform fault, and there is this divergent boundary right here by the Juan de Fuca plate. So it looks cool, but let's check out our other answers. Now, when we look at the Aleutian Trench, there's our key word, trench. And if I zoom in on the Aleutian Trench, I indeed have my symbol for a convergent plate boundary. That is why I want to go with the Aleutian Trench here, because I have my keyword and the symbol confirms that is indeed a convergent plate boundary. Okay, another snapshot of our gizmo. So convergent plate boundaries, they create a couple things. So what I've circled here is I have our direction of motion of our oceanic crust here. Our oceanic crust is moving towards our continental and is starting to dip down because that's our subduction zone. It is sliding underneath the continental. Now, when it slides underneath the continental, temperature gets really, really high the deeper you go into the earth. So what's going to happen to that crust is it starts to melt. And the reason we have volcanoes here is because we're melting that ocean crust. When crust melts, that magma wants to rise up to the surface, and we create our volcanoes from here. In addition to the ocean plate moving and subducting under the continental plate is getting pushed to the left as well. So while this continental plate is getting pushed to the left, we're building something interesting in addition to a volcano. This landmass right here, these are mountains, convergent plate boundaries. This collision of land is creating the buildup of mountains. The last topic I want to talk about here is this idea of hotspots. So a hotspot doesn't necessarily need a plate boundary, and we're creating volcanoes here. So a hotspot is going to be where we have a very large chamber of magma underneath the crust of the earth. So in our mantle, the very top, we have a huge chamber of magma, also called a magma plume. And that magma, being so hot, wants to rise up to the surface of the earth. So without having a subduction zone, we are having that rising of magma to create volcanoes. So what's cool about it is we have a bunch of these around the world, and we have our key down in the bottom. Now, one in particular that is asked about very frequently is the Hawaiian hotspot. Right smack dab in the center of the Pacific plate, there are no boundaries anywhere near the Hawaiian hotspot. So what this can tell us, or hotspots can tell us, is how the plate is moving. So when we look at Hawaii, in this picture right here, we have the ages of all the islands listed. We have Hawaii, which is our present island, at 0.5 million years old to present. So currently, this island has the magma chamber underneath of it, feeding the volcanoes on this island. In the top left, we have Kauai, which is 5.1 million years old. So What I can deduce about this situation is that Kauai, in order to form, used to be where Hawaii is now. To figure out the direction of plate movement, this is what you're going to do. You're going to take your youngest island, being Hawaii, and you're going to draw an arrow over to your oldest island, being Kauai. What this tells us is that the plate that these land masses are sitting on has moved to the northwest. There's currently a hotspot underneath of Hawaii that is feeding that island and that volcano with magma, just like it used to do to Kauai 5 million years ago. So Kauai used to sit where Hawaii was, but it was moved to the northwest because of the convection in the asthenosphere, and now it no longer receives any magma from the hotspot. In conclusion, there's a lot I need you to know here, and it really stems from this page. I need you to know the three boundaries: our transform, our convergent, and our divergent boundaries. And I need you to be able to use this key to find where they are around the world. So if you have any questions about tectonic plates, this map, even latitude and longitude, please talk to me. Please ask me a question. And I hope you have a wonderful rest of your day.